Alright, here we're looking at an example of a system of equations, and you can see already that this is an example where we have infinitely many solutions. And we're going to want to give the solution as an ordered triplet. Now, I know that there's infinitely many solutions here because this third equation reads 0 equals 0. 0x plus 0y plus 0z equals 0. And therefore, it's not contributing anything. So we only have two equations in a three-dimensional, or we have two planes in a three-dimensional world, essentially. So we know that there's going to be an entire line of solutions. And what we're going to do is we're going to parameterize the solution. What I mean by parameterizing it is deciding on a variable that will essentially say at some point along here our variable is equal to 0. At some point it's equal to 1. At some point it's equal to 2. Down here it might be negative 1. Down here it might be negative 2, and so on. When we're saying taking a parameter and putting our solutions to a parameter, this is exactly it. It's saying, okay, this point has a value of 1, this point has a value of 2, and so on. As far as actually choosing the parameter, our form here, this is essentially what we would have gotten if we'd plugged a system of equations into the calculator. It might have spit something like this out. And you'll notice that this row starts with a 1. And since this row starts with a 1, we can actually say that x has it's called a pivotal 1. That's a pivotal 1 there. This row starts with a 1. The y variable has a pivotal 1. But the z variable does not have a pivotal 1. It does not have a row that starts with a 1 there. So what we're going to do is we're going to say that z is the parameter. So this, saying we have a 0 here and a 1 here and a 2 here and so on, if we just go ahead and say, well, we're actually going to do that with our z-scale. This is going to refer to our location in the z-scale. Because that z does not have a pivotal 1, we know that this will work. And let's see why that's the case. This first equation says 1x plus 3z equals 2. There's a 0y in there as well, but whatever. We have x plus 3z equals 2. If I rewrite this so that it says x equals, well, let's subtract 3z from both sides, 2 minus 3z, then you can see if I give you a value of z, you can find the value of x based on this first equation. Similarly, for the second equation, that reads y, that looks like a negative, it's not supposed to be negative there, that reads y minus 4z equals 5. If I solve this equation, it reads y equals 5 plus 4z. I'm just adding 4z to both sides. And so if I tell you a value of z, you can similarly tell me a value of y. So taking all three of these together, also, maybe I should also say, if I tell you a value of z, you can give me, well, the value of z, clearly. So what I'm going to do here is I'm going to say no matter what value of z you give me, I can spit out values of x and y that satisfy these two equations. So that value of x is going to be 2 minus 3z. The value of y is going to be 5 plus 4z. And so this right here is called the parameterized form of the solutions. If z equals 0, we could actually evaluate, we could find out where on this parameterized scale, where z is equal to 0 just by plugging stuff in here. 2 minus 0 is 2, 5 plus 0 is 5, z is 0, so that's the point 250. But of course you don't have to say if z is 0. What happens if z equals 1? This would give us the point 2 minus 3, 2 minus 3 times 1, 5 plus 4 times 1, comma 1. So that's what, negative 1, 9, 1. This is another solution. So that's a solution to the system of equations. This is a second solution to the system of equations. This is the solution up here in my little graph, where z is equal to 1. And you can pretty quickly see that no matter what value of z you give me, I can just plug them into these two things, and I'll spit out another point, another point that satisfies this system of equations.